Hello. In this question, we're going to be exploring conservation of angular and linear momentum in an applied setting. So we have a horizontal rigid bar of length 2r. We look here, and this is the horizontal bar. It's pivoted at its center, so there's the pivot, like so. So either it's hanging from a string or it's leaning on a fulcrum or something like that. Free to rotate in a horizontal plane, and that is this parallelogram we see here indicating a horizontal plane, which means then that it can travel in a circle like that. We are given this as the indicative direction, so that's a positive omega. Point particle of mass m, so point particle means it has no dimensions. So we might think of r being equal to 0. That's going to be important for us later. It's attached to one end of the bar, and that's over here. We have mass m, and a container is attached to the other end of the bar. So there's some kind of basket or a container or a catcher or something like that. Then we have a point particle of mass m over 3 with a velocity v at right angles to the rod. So if it's at right angles to the rod, then we are looking at this. And it also means that it is traveling in this direction with a velocity v. This then should come as no surprise that that's a right angle. It's a 90-degree angle. So that's important because we see then this v then would be equal to the linear velocity of this at that particular instant right there. We have 90 degrees, so if there's a force applied to this at that 90-degree angle, then we've got a torque, and we don't have to worry about finding angles. So what's m over 3? Collides with the container and gets stuck in the container. So it's now entrained in this. It starts to rotate about the vertical axis with a positive omega. The mass of the rod and the container can be neglected. So the mass of the rod and the container are negligible compared to these masses. Now, just for perspective to compare these, if this mass here is m over 3, then this mass over here is 3m over 3. So we can see that this mass is 3 times as large as this one. So now we're asked to write an expression for the angular momentum just before the collision. Just before the collision. Well, it says that once it collides, it starts to move. So there's actually no motion at this point in time. There's actually no angular momentum. But at the instant before, this particle right here, this mass, m3, is right there. It's right inside that container. Right inside that container, like so. And what we know because of the law of conservation of momentum is that the linear momentum this possesses will become the angular momentum of this system. So the angular momentum will be equal to the linear momentum, but it needs to be expressed in angular momentum units. So we may recall we have some additional formulas that we make connections between linear and rotational world, where v is r omega and a is r alpha. And we know that torque is rf. So we have our linear on this side of the equation, r omega, and on this side of the equation, we've got our linear with the r. Well, it stands to reason then that the angular momentum would be equal to RP, which I've derived for you in a previous lesson and shown that that is in fact the case. So L is RP, and P is MV. So if L equals RP, and P equals MV, then we have MVR. And that is our relationship, except M is not, it's not M, it's M over 3. So we have L equals M over 3 V times R. And again, that's because the mass that is being, the mass that's coming from the linear momentum is M over 3. It's not just a generic M. So, while it's true in general L is mv over r, Rm is m over 3. So that is our expression for part AI. For double I, we're told it begins to rotate with an angular velocity omega, so that the angular momentum is equal to this. Well, let's start out with our definition of linear momentum, which is I omega. Now, the moment of inertia is generically, mr squared. So you have mr squared omega. But again, the mass isn't just an m. We want to know in this particular case, what is the mass? Well, in this system, we have the mass that resides over here and this mass over here. And lo and behold, we had already defined these as 3m over 3 plus the m over 3 r squared omega, which then becomes 4/3 m r squared omega is L. And if we check what we're looking for, that's indeed exactly what was being asked for. In part 3, we're now asked to show that omega equals V over R. So in the previous question, since these questions one builds on the next, we know in the beginning that the angular momentum, the expression we just came up with, is 4/3 m r squared omega. But we know that that momentum came from this initial linear momentum. And so that is also equal to mv over r. Now, you might wonder why I put in this second relationship. So if we took this relationship that we just had from the previous part 3, and solved for omega, there would be an L in there. And notice in the answer, there's no L. So we've got to get rid of L somehow. So since all of these are fine, it's the L we need to get rid of. We need another expression for L. We went back and looked for it, and that's what was in part 1. Well, now doing some, it's m over 3 r. It's m over 3 VR, excuse me. So we can multiply the whole thing by 3, and that's going to give us mvr equals 4mr squared omega. And then omega is mvr all over 4mr squared. The squared goes away, that r goes away, the m goes away, and we are left with v in the numerator and 4r on the bottom. And so that is part 3.